In this video, we're going to discuss inner product, vector length, and distance. The inner product of two vectors, which is sometimes called a dot product, is simply multiplying the transpose of the first matrix by the second matrix. So a couple of things to point out. First of all, I want you to note the notation. We just have the dot in between. That's to denote that we're finding the inner product or dot product. And again, all we're doing is we're taking, if we're finding u times v, or the dot product or inner product of uv, then I'm going to be thinking about this as 4 to negative 1, 0 times 3, 0, 1, negative 1. And if you'll notice, this is a 1 by 4, and this is a 4 by 1, and that means, yes, they can be multiplied, and the result is a 1 by 1 matrix. So what's going to happen is I'm going to take 4 times 3 plus 2 times 0 plus negative 1 times 1 plus 0 times negative 1. And it's just going to end up as one value. So that's 12 plus 0 plus negative 1 plus 0. And so my result is 11. I also want to point out something that hopefully was pretty obvious as we started here. Yes, technically what I'm doing is I'm taking u and finding the transpose, but really I don't need to write it out like that, because what am I going to do? I'm going to take 4 times 3 plus 2 times 0 plus negative 1 times 1 plus 0 times negative 1. So if it were me, and I'm lazy and I don't feel like writing out the transpose, really we're just multiplying component-wise, so we're matching them up. And that's why they both have to be the same dimension, n by 1, because if they're not, obviously we wouldn't be able to multiply them. Here's a practice for you to try. I want you to compute the inner product of u times v and v times u for the two vectors given. When you are done, press play to see how you did. So again, if I'm computing u times v, then technically I'm taking u and turning it into 0, 1, 2, and I'm keeping v exactly as it is. But remember, we just talked about the fact that it's not necessary to write them in that way, because all I'm going to be doing is multiplying component-wise. So this result is going to be 0 times negative 3 plus 1 times 3 plus 2 times 2. And again, I am writing it in a vector. It is a solution, a 1 by 1 vector. And that gives me 0 plus 3 plus 4, so my solution is 7. Now I also asked you to compute v times u. And again, what's going to happen is I'm going to get negative 3 times 0 plus 3 times 1 plus 2 times 2. And obviously this is exactly what I just did, so I'm going to get 7 again. So this is not a proof, however it's a great example to show you that the inner product of two vectors is in fact commutative. In addition to the commutative property that we just talked about, we also have a few other properties. So the first says that if you have the sum of two vectors and then multiplied, or the dot product of the sum times some other vector, I can go ahead and distribute just as I normally would. So I can take the dot product of u and w and add the dot product of v and w, and I will get the same result. The third property tells us that if we have some scalar c, and I have the scalar multiplied by, say, vector u, and then I'm taking the dot product, it's the same as me taking the dot product of u and v and then multiplying by the scalar, or the same as multiplying that scalar by v and then taking the dot product. All of those things are the same. The last one is the sort of craziest one, I guess, and the only one that really requires us to think about it in a little more depth. It says that the dot product of u by u is greater than or equal to 0, and also says that the dot product of u with itself is equal to 0 if and only if that vector u is the 0 vector. So let's look at this one, because that might not be immediately obvious, and maybe it is, and if so, that's great. This is saying that I'm taking u by u, which essentially means I'm taking all of those values or entries inside the vector. So this is just going to be, say, u1 squared plus u2 squared plus u3 squared plus, oops, not a, un squared. And obviously that is going to be a positive product because we have everything squared. So whether or not those entries are positive or negative, when I square them, they will become positive. So that's where the greater than or equal to 0 comes in. And then obviously we can see that it would only be 0 without much thought if and only if the vector itself is the 0 vector. The length or norm of a vector is the non-negative scalar, and it's defined by essentially taking the square root of the inner product of a vector by itself. So we can look at this two-dimensionally, and it can make perfect sense because two-dimensional is obviously an easy way to visualize. If I have vector v is AB, then this is vector v, and I'm trying to find this length. Well, if I'm trying to find that length, then I know that I can take a squared plus b squared, and that's going to give me v squared, or the length of v squared. So I want to just know v, so I'm going to take the square root of a squared plus b squared to give me the length of v. And that's all this is telling us. So obviously I've shown you in a two-dimensional example. This says it works for however many dimensions that you want, and it's still going to give us the length of that vector. So now let's take a look at distance, because that's what we're really interested in. If I want to find the distance between two vectors u and v, and again, if I'm talking about distance, here's u and v. This white line that I've drawn in, that's the distance. I want to find what's the length of that segment, which is the distance between u and v. So I want you to think of this as u plus negative v. So this guy right here, negative v. And we know, using the parallelogram rule, that if I want to find the distance, or if I want to find just u minus v, then it's going to be that guy right in the middle in the parallelogram. And so if you'll notice, something very interesting is happening, that this u minus v distance is the same as the distance between u and v. So it makes another parallelogram. And so that's essentially what we're saying, is all we're going to do is find u minus v and find that length, and that's going to be the distance between u and v. So let's do an example. We're trying to compute the distance between vector u and v. For u is 3, 2, so this guy is, oops, I need to choose a color other than white. This guy is u, and v is negative 1, 4, so this guy is v. And if you'll notice, I've also labeled u minus v. So essentially what I'm going to do is I'm trying to find this distance in black. That's what we're asked to find, is the distance between u and v. But that corresponds to this distance in green. It's the same distance. And so all I'm going to do, using my formula, and if you'll recall, we just wrote that distance uv is equal to the length of u minus v. And so all I'm going to do is then find u minus v, which would be very easy to compute. So 3, 2 minus negative 1, 4. And that gives me 4, negative 2. And again, that's where this guy came from, is 4, negative 2. So that's really just u minus v, which we can see visually on our graph, but we can also compute very easily without graphing it. What I'm now trying to do is find the length of u minus v. And again, the length of u minus v is just going to be the square root, in this case, of 4 squared plus negative 2 squared, because that's the formula we talked about for length. So it's just kind of like the Pythagorean theorem. So that gives me 16 plus 4, and so the answer is radical 20, and that is both the distance from 0 to u minus v and also the distance between vectors u and v. Here's a question for you to try on your own, so press pause, try this question, then press play to see how you did. So here I'm just asking you to find the distance between u and v, and obviously we're working in R3 now. All I'm going to do first is to find u minus v, and that's going to help me to determine the length of uv, which is the distance between u and v. So u minus v would be 764 minus negative 2, 3, negative 1. And again, we're subtracting, so 7 minus negative 2 is 7 plus 2. 6 minus 3 is 3, and 4 minus negative 1 is 4 plus 1, so 935. To find the length of u minus v, which is equal to the distance, I'm just going to find the square root of 9 squared plus 3 squared plus 5 squared. I got a little overzealous with my square root. So 9 squared is 81, 3 squared is 9, 5 squared is 25. I add those values together, I get the square root of 115, and that is in fact, therefore, the distance between u and v, which is the same as the length of u minus v.